Hey guys, today's content is pretty much the last exercise within the matrices topic. This one will probably run over 2 lessons as it is quite large and it is pretty hard as well. Now, this one isn't in your textbook. This is an additional resource, let's try that again, which you'll find in your class news feed down the bottom called under Transition Matrices worksheet with answers. Now, transition matrices, for those of you that did year 10 in general, you would not have touched on this at all. It is a brand new concept to you. It is usually taught mostly in year 12, so it is quite hard and quite challenging, but we are going to expose you guys to it. Now, in transitional matrices, we need 2 pieces of information. And it is one of those ones that you get better at with practice, like with everything. The way I'm going to do these notes is mostly through examples and explaining in step-by-steps as we go. Alright, so what we need is something called the initial state matrix. Now it's usually denoted by this symbol, S0, S being the state, 0 being the beginning, so it's where it initially starts. So that's the information that we usually start with. Number 2 thing we need is the actual transition matrix. That shows us how the information is changing over time. And depending on the context, it could be in days, weeks, months, years. But we'll go over some examples. And that's usually just denoted by a simple T. Alright, so a lot of these ones are worded problems, so we are going to be going through a couple of those and being able to actually work out the information. First example we're going to do is a network. Alright, so copy it out first and I'll explain what it actually means. Alright, this question, and this is in the notes section down in the class news feed. You see the document says matrices notes. This is in there if you ever want to have a look at it. This is a car rental company. They analyse the movements of their cars between 2 suburbs. Here we've got Bendigo and we have Colac. So they were looking at how the cars moved between those 2 suburbs. What they found was for the cars in Colac, at the end of every week, 90% of those cars ended back in Colac, 10% of them ended up in Bendigo. So they've got 2 branches, one in Bendigo and Colac. 90% of the cars that were picked up in Colac ended there, 10% ended in Bendigo. For the cars picked up in Bendigo over a week, well after a week, 80% of them ended up in Bendigo, 20% ended up in Colac. Now the information in the diagram here is how we're going to create our transition matrix, because this is showing how it's changing over time. After 1 week, 20% of the cars are going here and 10% are going here, so there's been a lot of changes. At the moment, we don't have the information for our initial state matrix. We don't know how many cars we're starting with or anything, but with this information, we can work out the transitional matrix. So we'll have a go at that. Now, it is going to be a 2x2, and typically with all transitional matrices, they are going to be 2x2. I will need a bit of space for this one, so I'm just going to write it here. All right, now, with these, our sides will be labelled. So it could be B and C or Bendigo and Colac. I'm just going to use B and C. At the top here is where the initial, or where it starts. On the side is where it will end. So in the context of this question, where it's rented in, where it's returned to. Now, two suburbs of Bendigo and Colac, so this is the way we label it. Alright, now we need to put this information into here. Alright, let's start over here. This 80%, so these four values are going to be our four elements. We just need to work out which ones go where. 80% that started in Bendigo, end in Bendigo. So that's this space here, the first element. 80% start in Bendigo, then finish there. With these transitional matrices, it's better to represent them with a decimal rather than a percentage because we are going to be doing some multiplying. So I'm going to write 0.8. Over here, 90% that started in Colac, end in Colac. So I'm going to put 0.9 there. Now just a little tip, sometimes that's all the information you're given, but with these, the columns always have to add up to 1. Alright, so with a transitional matrix, or 100%, they have to add up to 1 or 100%. So here, 20% that start in Bendigo, end in Colac, so here's 0.2. Here, we've got 10% that start in Colac, finish in Bendigo, 0.1. So make a note of that somewhere in your books. The columns in a transition matrix always add up to 1. That's the first piece of information that we always need to work out. Sometimes it's represented in a diagram like this, sometimes it's given to us in a worded form, which is the next one we're going to go over. Alright, extending on to this one, let's say at the start, or initially, there were 50 cars in Bendigo, and 40 in Colac. Alright, so now we've got information to create our initial state matrix. The way we write this is, alright, S0, where we're initially starting. Initial state matrices are always 2 by 1, so they always have 2 rows of the 1 column. Over here, we did Bendigo then Colac, so we're going to be consistent here. We'll do Bendigo then Colac. In Bendigo we had 50 cars. In Colac we had 40. Alright, so that's our initial state matrix. That's the information that we're starting with. This matrix, we can use that to manipulate this one to show how it changes over time. As long as these changes are consistent and keep happening week by week, we can use that to work out how many cars are in each place each week. So let's say we wanted to work out after 1 week. That would be what we call S1. So instead of S0 being at the start, S1 would be after 1 week. Depending on the context of the data, it could be after 1 month, it could be after 1 year, but it's always stated in the question. Now, what we do is we take our transitional matrix and we multiply it by the initial state. Alright, so if we do S1 equals T times S0, that'll give us how many cars are in each place after 1 week. After we've worked that out, we could do S2. So that T just keeps getting multiplied by the previous state matrix, and it kind of tells us how it's changing over time. With these ones, we never really have to do them by hand. They're always done on the CAS. What you would do is you would save that as T in your CAS, and then you could save that one as S or something. Just to show you, if we did work this one out, S1, so if we went T times SO, so that times that, what it comes out to is this. We would round it to a whole number because we're talking about cars here. And it would show us that some of the cars that have left Bendigo have gone to Colac, so after 1 week, 44 cars in Bendigo and 46 in Colac. If we did it again, you'd notice a trend, you'd notice that the Bendigo ones are going down, you would notice that the colac ones are going up. So that's how to find it after 1 or 2 weeks. Now, sometimes you'll get a question, for example, that says, all right, how about after 1 year? It would take us a long time to do that 52 times. So we need a bit of a shortcut. And that's where this rule comes in. A rule for finding the state matrix after n steps, n representing the unknown number. So Sn, that n could be 100, could be 200, we don't know. We go the transition matrix to the power of whatever it is we're trying to find. So if it was this question and we're trying to do it after 15 weeks, we would do that to the power of 15 times by the initial state matrix. So what that can do is that can help us find something down the track without having to find all the previous ones before it. There is a little bit more content to go over here. What we're going to do is we're going to go through a large example and make some notes for it as we go through. Now, in that handout, the one under the class newsfeed on transition matrices, this is question 2. So you don't need to write this out. We're going to go through question 2 and go through some stuff as we go. Unless you want to write it out, it might be a good idea because we are going to go through some of the notes. All right, so the question says, at a large retail outlet, 2 types of milkshake are produced. 45% of people drink chocolate, 55% of people drink strawberry. Research shows that of those who drink chocolate, 35% will change to strawberry, and those that drink strawberry, only 5% will change to chocolate. So, question A says find, or what is the initial state matrix? Now this one's different. We're not given actual numbers of people that drink each type, we're given a percentage. So we're given that 45% of people drink chocolate, 55% of people drink strawberry. So that's the information we're going to have in our initial state matrix. So it's important to be able to differentiate between the percentages in our initial state matrix and our transition matrix when you're given a question like this where it's only percentages. All right, where it's talking about change, that's where we know it's going to go in our transition matrix, but where it's just talking about facts about how many people drink each type or whatever the question is, that's our initial state. All right, so 45% of people drink chocolate. No, this must be a fake one because chocolate's much better than strawberry. And 55% drink chocolate. Again, that's percentages, so the column would have to add up to 1. Now, question B. What is the transition matrix? These two are the hardest parts of the questions. Once you work out what the matrices are, it gets easy from there. All right, so transition matrix. It's going to be a 2 by 2. Remember, this is where we start, this is where we end. So what the question says, research shows that 35% that currently drink chocolate will change to strawberry. So starting at chocolate and changing to strawberry is 35% or 0.35. And then those that drink strawberry, only 5% will change to choc. So starting at strawberry, changing to choc is only 5% or 0.05. Now this is what I was talking about before. We're only given one piece of information in each column, but they have to add up to 1 so we can fill in the gaps. So something to 0.35, which in this case is 0.65, and here 0.95. So So that's our transition matrix. That shows us how the information is changing over time. Now that formula I showed you before, t to the power of n times the initial state, that's the one you only really ever need to use. So, question C. What proportion of people will drink each type of milkshake at the end of 1 month? So this, in the context of this question, the time is months. So we want after 1 month. So S1 would be t to the power of 1 times the initial state. I'm not sure what that is off the top of my head. If you type that into your CAS, you would hopefully get that. Oops. .32 for chocolate and 0.68 for strawberry. So what that means is that after 1 month, based off this information, we expect 32% of people to be drinking chocolate, 68% of people to be drinking strawberry. Now if we look at the next one, after 2 months, and I think E is 3 months. I'll write them out, I'm not going to fully work them out. After 2 months, we would write it out like that. So t to the power of 2 times the initial state for 3 months. T to the power of 3 times the initial state. So it gets a little bit repetitive, but it's not that hard, this part. The actual setting up of the matrices is the important part. If you stuff up a number in there, it's going to ruin all your calculations. Now, F and G have much larger numbers. So what proportion of people will drink each type of milkshake at the end of 100 months and then at the end of 101 months? Let's start with F. So the way we write that is 100, so t to the power of 100 times the initial state. All right, if you were to solve that, you would get this answer. 0.125 and 0.875. If you converted that to a percentage, what that means is after 100 months, you would expect 12.5% of people to be drinking chocolate, 87.5% of people to be drinking strawberry. Now with G, very similar, 101 months. You'll notice something pretty interesting about it. If you type that into your CAS, you'd actually get the exact same answer as the previous question. What that means is, this is related to question G. Question G says the steady state matrix. What proportion of people, what is the steady state matrix? After a certain amount of time, if you get into numbers this high, the matrix, the state matrix that you get as your answer will actually not change. It'll get slightly and slightly smaller, the changes between each number, until it gets to a point where it can't change anymore. This is called the steady state matrix. So steady state matrix is after a long period of time. So after a long period of time, the state matrices don't change. So they get to a point where they just stop. If you ever have a question which asks you for what is the steady state matrix, so it might not say 100 and 101, it might just ask for the steady state matrix. What you need to do is pretty much make up a big number, it could be 100, it could be 1,000, doesn't really matter, and you put your transition matrix to that power. So if you had this question but it didn't ask for that, you might put, all right, t to the power of 500 times initial state. The important thing though is that you do the number after that to make sure it hasn't changed. So you might say, all right, I'm going to do t to the power of 200 times SO, I get my answer, then t to the power of 201 times SO, it's the exact same answer, that means I conclude that that is the steady state matrix. So to test for the steady state, so to test for steady state, use the Tn times SO formula and sub in two large values for n. If they haven't changed, that means you've found the steady state. If there's like a 0.001 difference, go a little bit further and keep going until you have no changes between the state matrices. So that's pretty much transitional matrices. It is quite tricky. Have a look at the handout. Make sure you're looking at the answers if you're not sure how to get it, and try and backtrack from there. If you are really struggling though, as per usual, use the Google Classroom.